All right, well, let's go ahead and get started. So I just want to give everyone a big welcome to the Fall 2020 compiler course. Hopefully you've been waiting your whole undergraduate career for this course. In some sense, it's a culmination. We're going to use lots of things you've learned, all the way from things you learned as maybe freshman or sophomore in 211, and things you've learned more recently, maybe in 311, as well as even some of the discrete math, graph algorithms and things. And it all comes into play in the compiler course. Just quickly introduce myself. I'm Jeremy Seek. I'm a professor here at the Luddy School of Informatics. I was just appointed a full professor, which means I'm older than I look. I do a lot of research in programming languages, trying to improve programming languages. One of the main things I've been doing over the last 10 years is something called gradual typing, which is looking at creating languages that let you have static typing like Java or dynamic typing like Racket, sort of under your control, under the programmer's control, so you can choose when you want to have which. And it sounds like a kind of a simple, easy idea, but it turns out to be challenging to make this work out in practice for lots of languages. Yeah, so I teach a compiler course. You'll be using a textbook, a free textbook that I wrote and had lots of help with from prior students and AIs over the last, quite a few years, putting that together. And then I just want to introduce Jenner. Maybe Jenner, you could go ahead and Jenner will be the assistant instructor. So go ahead.
Hey, how you doing, guys? Hi, I am Janar Diriji, and I'll be your TA in this class. I'm a fifth-year PhD student at IUCS, and I'm working on programming languages as well. And in fact, Jeremy is in my committee, and I've been researching about JIT compilers, just-in-time compilers, and very excited to be here. And this was actually one of my legit most favorite classes of all time. It's so much fun. I hope you're excited too. So, and I'll be available almost all the time on Slack, like 24/7. So whenever you have a question or whatever, I'm sure Jeremy's going to explain.
You gotta sleep sometimes, man, because so that you're at the top of your game, so you give out good advice to these compiler students.
Yeah. So yeah, I guess you can talk about like the availability and stuff. I'm sure Jeremy's going to explain all those things. Mm-hmm. And yeah, I feel excited.
Yeah, cool. Maybe let's just quickly go around and everyone can say their name. Maybe I'll say their name and maybe a sentence or two about themselves. I guess I should maybe call out your name or try to pronounce it so you know which order we're going. So how about Sam? You're next in the grid on my Zoom.
All right, can you hear me?
Yep.
Yeah, I'm Sam Susi. I'm a senior in CS, specializing in programming languages. Yeah.
Welcome. All right, Zach.
Hi, I'm Zach. I'm a senior studying computer science and math. My CS specialization is AI. And yeah, that's actually it. I thought I had more to say, but I don't.
That's all right. You can save it for later. All right, Franklin.
Hi, I'm Frank, a senior, also in programming languages.
Great. Nice to meet you, Frank. Okay, Drew.
Hi, I'm Drew. I'm a senior as well, and I study biology, computer science, and math, and then my CS specialization is artificial intelligence.
All right. All right, Alice.
Hello, I'm Alice. I'm a senior undergraduate. studying programming languages, and I am a perpetual employee of Professor Ken.
Very good. Aditya.
Hi, I'm Aditya. I'm a second year master student. So I try to specialize in programming languages and cloud computing.
All right, Grant.
Hi, I'm Grant. I'm a senior computer science student. Just switched my specialization from security to programming languages. Yeah.
Great. All right. QA.
Yeah, here I am. Yeah, it's
And
QA.
could you pronounce your name for me so I get it right next time?
Yeah, it's correct. It's just QA. Yeah.
QA. Okay.
I am the second year master, major in computer science. Yeah.
Great. Welcome. All right. Key.
I'm Kai. I'm a senior specializing in programming languages. I also am getting a degree in music as well.
Wonderful. Welcome. Okay, Connor. Oh, Connor's muted or. Oh.
I'm a senior in computer
There we
science with a specialization in programming languages. I work in the Career Services Office as a mock technical interviewer and peer career advisor.
All right. Welcome. All right. I'm going to skip John Yu. Oh no, we'll say hi to Chan Yu. Hello, Chan Yu. Chan Yu is a grad student who's just hanging out to enjoy the fun.
Yeah. Hello.
All right, David.
Hey, I'm David. I'm a computer science a senior computer science major with a specialization in programming languages.
Great. And Zhao Zhang?
Yes. Hi, I'm a first year graduate student. I'm specializing in artificial intelligence.
Great. Alex?
Hey, I'm a PhD student open ISE in cloud engineering.
Welcome. Kevin?
Yeah, hello, my name is Kevin. I'm a senior in computer science and also have a specialization in software engineering.
Great. Elijah?
Hi, I'm Eli. I'm a junior in ISE, concentrating in cyber-physical systems.
Welcome. W. Lamb? Let's see, is that? Huh. Maybe that's nobody? Okay, and then last, Joel Hudson. Joel? Hello, Joel. Oh, well, we got most everybody. Okay, right, so let's move on. So maybe a little bit more background about this course. It kind of goes pretty far back. I took the course around 2000-ish as a grad student here at IU from, oh gosh, I'm blanking. Oh, this is terrible. I'm blanking on the professor that I took it from. Kent Dybvig was the name. And that was an awesome course. He, you know, a lot of the current course is inspired by what he did. And he was a real expert in compilers. He implemented the Shea Scheme compiler, which is one of the most efficient implementations of Scheme out there. And so I took the course from him. At the time, the course was, I want to say it was either front to back or back to front, one of those two. Over the years, the compiler course has done it both ways, front to back and back to front. This year, and the way I've been doing it more recently is what I call incremental, which is sort of neither front to back or back to front. It's you grow the language a little bit at a time. With every couple weeks, we have a project that's due, and we keep growing the input language, and then with each input language, we do the whole compiler all the way from the input, which is going to be a subset of Racket or typed Racket, and the output is x86 assembly code. So we're going all the way down to to the metal, and so you're going to see the whole thing. There's no magic. Right now your idea of what happens when you run a program, it's maybe a little bit of magic, but we're going to sort of look under the hood and see what happens exactly, and so you'll be able to see it all. Right, so we'll be doing that incremental approach. You'll be living with your own code all semester, which might be a little bit of a different feeling from other classes. It's not like you submitted a homework and then you never have to see that code again. Instead, what it is you'll be submitting your project 2 weeks in, and then you're going to build on that for the next 2 weeks, and then you're going to build on that for the next 2 weeks. So you kind of have to live with your code the whole time. So this becomes also a great course in just software engineering, and that's why one of the reasons why I like this course so much is that you get a lot of practice with your software engineering in addition to learning all about compilers. All right, so I want to kind of just do a high-level overview of what we're going to cover in the course. Basically, I'm just going to pull up the table of contents of the book. Here, I'm going to share my screen. All right, so hopefully you can see the book now. Essentials of Compilation. Those are a lot of people that have contributed to it. So the first project is really coming in chapter 2 there, integers and variables. Today we're gonna talk about a lot of the things in chapter 1. But in chapter 2 is where things get serious. We'll introduce this little language called R1 that has integers and variables introduced with let binding, and arithmetic like addition and negation. And then we're gonna go through a bunch of compiler passes, phases of a compiler, all the way down to x86. Okay. If you're a grad student, or if you have a grad student in your group, so we're gonna be doing this in teams. So we're gonna be having teams of two to four people. But if you have a grad student on your team, then you also get to do the challenge assignment, or you have to do the challenge assignment. If you don't have a grad student on your team, you can also do the challenge assignment for fun and extra credit. Okay, so integers and variables is where we start. Then we're going to dive into register allocation. So in that first chapter 2, we're gonna sort of go the easy way and avoid this thing called register allocation. But then the second chapter, we're going to get into that, and we're going to make really great use of registers on the computer to make things go faster. Then in chapter 4, we're going to add Booleans and control flow. So you'll have like if expressions, conditional expressions, and branching in your programs. And so that adds a fair bit of complication to the compiler. After that, we'll be adding what is in Rackets called vectors, or what also is commonly called tuples to the language. And that's actually will be the first time we have something that's allocated on the heap. And so things on the heap can last forever in this language in Racket. And so the implementation really needs to have a garbage collector. So we'll talk about garbage collection. I think I'll do what we did last couple of years, where I won't ask you to implement the garbage collector itself. That's a big pile of C code, but you will have to interface with it, and there's a bunch of things the compiler has to do to talk to the garbage collector. In chapter 6, we'll add functions, as in sort of kind of C style functions with and function pointers. And then, or top level, they're just top level definitions of functions. And then in chapter 7, we'll add lambdas. And that's probably where, that's sort of like, in some sense, the culmination of this course. If we get beyond that, that's sort of icing on the cake. We may try to get to the dynamic typing part of it in chapter 8. We'll kind of see how it goes. You know, obviously, with COVID and all this crazy stuff happening in our lives, you know, we're gonna need to be a little bit flexible this semester, and so I'm not dead set on going as fast as possible the whole time. If we need to slow down a bit, we can. All right. Okay, so that's sort of just an overview of what's going to happen in terms of the languages. Any questions about that at this point? Okay. Okay, so the next thing I want to talk about is just some administrative kinds of things for the course. You know, what the grading will be like, the assignments and stuff like that. So like I mentioned, it's just this big project is the whole course. Roughly every 2 weeks, an assignment will be due, where you're finishing basically one of those chapters in the book. If you look at the overall, so we'll also have quizzes. So basically like the week after you submit an assignment, we'll do a quiz. And really the quiz is just geared towards like, you know, did you learn, you know, everything from that book chapter, that assignment, okay? And one thing I should say on sort of the academic integrity front is that when you're doing the compiler implementations, it's what I'll call no holds barred. Okay, you know, the term from wrestling. Okay, so do whatever you want. Okay, talk to whoever you want. Look at other people's code. I don't care. Okay, whatever helps you best learn. Okay, personally, I like to write a lot of code and sort of fight with it myself, and then maybe when I get stuck, talk to a friend. And you know, when I'm teammates, sometimes I like to pair program. That's a fantastic way to avoid bugs. You'll probably discover in this course that you spend maybe a quarter of the time writing new code and then like 3/4 of the time debugging that code. Okay, and if you're there pair programming, oftentimes, you know, the person who's not actually typing at the moment can spot mistakes and sort of keep asking you why you're doing what you're doing, and usually that reveals that you're doing something that isn't quite right, and you know, and then you can fix it. So whatever you want to do with assignments, you know, no holds barred. I mean, if you're asking questions on Piazza, that's what a little getting ahead of myself, but on Piazza is how we're going to do email group for the class, and you can ask me questions and Jen R and each other, and you can answer each other's questions on Piazza. And if the best way to express the problem that you're encountering is to paste some code in your Piazza post, that's fine. Don't worry about it. In fact, that's probably encouraged because oftentimes questions can be hard to understand without the appropriate context. Okay. But then after the assignments, there's quizzes. So the quizzes are sort of a check on like, okay, did you learn what you need to learn in the assignment? And then we'll also have a midterm and a final exam. Okay. And the idea is that if you do the assignments and it, let's say you break it up among some teammates, but then you talk to the other teammates, look at their code, and really understand what the whole thing is doing. If you do all that, you'll be fine on the exams. Okay. Okay. Then any questions about that? Okay. Oh, and I guess I should mention we're going to use the modus respondus or some. I might be killing the name of that proctoring service, but
Respondus Monitor.
Respondus Monitor. I'm getting it confused with the name of a particular Indian Pale Ale from Colorado. Anyways, okay, so okay, let's talk a little bit about the technology that we're using. With the online course, we got a lot of technology. One thing I'm trying to do is diversify the technology, which is slightly annoying in that you just have to deal with more technology, but maybe it's going to be better because if one technology goes down, we'll have backups, unlike all the courses that were using Canvas yesterday. We are using Canvas. Right now, the only things on Canvas is that it has a link to the real homepage, and it has the graded book. Okay, it's perhaps the easiest way for us to post your grades. So that the plan is still to post grades there. Though if that doesn't work for some reason, I do know of a good backup. We can use IU Google Docs shared per student, I guess, would be the way for us to do that. Okay, so hopefully you've already seen the web page. It's actually hosted over on GitHub. That's the main place you want to look for, like assignments, due dates, resources, stuff like that. Okay, if you haven't already, go and sign up to get on Slack. The Slack is there mostly as a sort of backup when like things go wrong. My daughters are in, well, one's in elementary school, one's in junior high, and they have been doing online learning with the, you know, the local elementary schools and stuff the last week and a half. And it's been like super frustrating. Like things go wrong and then there's no way to like contact the teacher to know like, are we doing something wrong or did the teacher do something wrong? And why can't this meeting start? You know, kind of things. And so hopefully I'm going to have Slack open and ready to roll so that if you're having trouble of any kind or wondering what's going on, I'm only a few key presses away. It's also there just for any other kind of questions you might have. Basically, that Slack is nice when you want some sort of real-time back and forth conversation. Whereas if it's more of a sort of a long question and maybe the response is going to take some thought, then that's better for Piazza. Okay. All right, so lecture video. You're here, you're on Zoom, that's working, awesome. I do have a Google Meet set up as a backup. So for example, if Zoom were to go down, the first thing I would do is I would type on Slack saying, hey, I just lost connection to Zoom. And then I would probably check my internet, see if my internet's down. Actually, if my internet's down, I don't think I have a good backup for that eventuality. I guess you know what I would do? Actually, I do have a good backup. I've got my cell phone. I can in Slack on here, so I can type into Slack and tell you that you know, class is canceled for the day or whatever, if my internet's down. Or if it comes back up, I can then, you know, message you to say it's back up. Right. So yeah. So if the Zoom goes down, you know, we'll be in contact on Slack. Maybe try to get Google Meet going. And then the other
question about that.
Yeah.
Are you gonna make I see that you're recording this. Are you gonna make the lectures available offline as well?
Yes. Yes. The administration likes us to do that, and I think it's just a good idea for, you know, maybe one of you have an internet, you know, the internet goes out in your house or whatever, or we also have some students in different time zones. And so having the option to watch it after the fact is nice. Also, sometimes it's just nice to be able to go back and review some part of a lecture. Maybe, you know, Jeremy talked too fast and you can just go back and watch it more slowly. Or maybe you're prepping for the final exam or the midterm exam and you want to go back and watch something. So yes, it's being recorded. It'll, you know, after a little, you know, usually I can get it up about a day after. I think I'll probably put the links on our course webpage. Okay. Okay. Any other questions so far? Good question. All right. So then the one other piece of technology, we're going to be using GitHub quite extensively. You'll be using GitHub to turn in your assignments, and hopefully for even more than just turning them in. So hopefully you'll be using GitHub to develop your code. In fact, one of the best ways to sort of, if you want, like let's say you've come to office hours and you've got a question about your code, it's really awesome if you have your code already pushed and on GitHub, and then I can just pull it down onto my computer. I can run your code, and see what's going on and really understand the situation, and then give you good advice based on what I'm seeing happening. Okay, so what I would encourage you to do is to get on, make your GitHub repo as soon as possible, like do it this afternoon, and then send Jenna and I an invitation. Okay. I realize that maybe some of you maybe don't know or haven't used GitHub yet. In that case, maybe what I would suggest is during office hour, come to an office hour with either Jenna or myself, and we'd be happy to help you get started with GitHub. Also, there's lots of tutorials out there on GitHub. So maybe the first thing to do is to do maybe one of those tutorials, and then if you still have some questions, then you can ask Jenna or myself. But GitHub's a great tool to, or source version control in general is a super important tool to know about for someone doing computer science, software engineering, etc. And so. Yeah, so hopefully we won't, we'll have to worry about dogs eating people's assignments. My dog's name is Ginger. She's a golden retriever. Maybe I'll get her up. She's not supposed to come upstairs. That's why she's not here with me. If I was in Luddy, she would be there with me. But anyways, hopefully we'll get her up here later, even though she's not allowed upstairs.
Quick question.
Yes, Sam.
So will the repos be kind of per group?
That's a good question. I think there's sort of two different ways we've done it in the past. One is just like a repo per person, and if you're in a group, you just have duplicates of it. And the other option is to have it per group. I don't know, Jenna, you're going to be doing the grading. Do you have a preference?
I think what we've done before was when I was taking the class, we were doing like one person in the team was keeping the repo, and the other person on the team was just a contributor to the repo. And what we've done was we've sent particular commit links to that repo as a submission from only one repo, and maybe in the commit message, I think what we've done, we've written in the commit message the team members and the grader was. I think what I would like personally, I would like to get one submission from each group, and I can keep track of the group members. That's no problem for me, but it might be confusing if there are duplicate repos for each group because may not be synced and update issues.
That's a good point. Yeah, and I will be asking you to make sure to have like a README file in your repo with like the group members listed there, just as so it's easy for everyone to know what's going on. So okay, well that sounds great. So just one repo per group. All right. Okay. One thing I want to make clear is that technology glitches, are not going to going to have an effect on your grade. Okay, so like, you know, when things are going, you know, when technology fails and things are going wrong, maybe GitHub goes down, and it's like the day of that the project is due, and no one can submit their project, right? You know, what I'll do is I'll be like, okay, GitHub's down, the due date's pushed back, right? So we'll be flexible, we'll work around it. And the last thing I want is for people to get bad grades because of some technology issue. Okay, so deep breath. Hopefully that you know, that makes you a little bit more relaxed. All right, I think that does it for administrative kinds of things. And the next plan is to dive into some actual content. And I need to double check the time here. I think, what do we go to? Is it 4:30? I should have a... Just double check when we finish up here. Yeah, 4:30. Okay, so we just have a good chunk of time left. Okay, any questions about sort of the administrative side, grading, assignments, stuff like that?
I actually have a question. What will be the formats of the quizzes? Like, is that going to be like similar to midterm and final exams?
Yeah, that's
going to record
traditionally. One thing I'm trying to decide on is whether to do sort of more like what quizzes would look like if we were doing them on paper versus trying to use Canvas quizzes. And Canvas quizzes, what I've found is that basically they only work for multiple choice and that's it. And that's kind of restrictive. But if it's just sort of a quick checkup kind of thing, then maybe it's okay. So I think I need to think about it some more as to whether I just want to do sort of multiple choice quick checkup kind of things, or whether I want to go a little bit deeper, in which case, you know, we would probably do, you know, you'd probably do your quiz on a piece of paper and then like snap a picture and upload it or something. So was there a question? I think maybe I saw a hand or no. Okay. Okay. All right. Well,
oh, sorry.
Oh, go ahead, Franklin.
So when it comes to the groups, I kind of have like, I guess, two questions about it. Are we supposed to form those ourselves?
Yes. Go ahead, you know, and I think what I'll do is I'll let you guys go at it for a couple days. And then if there's still sort of, you know, if we don't have a good set of groups covering the whole class, then I'll help out and we'll try to shift things around or get some groups formed. One thing I would recommend is that, so many of you have lots of Racket experience, programming in Racket. I think there might be a few of you that don't have experience programming in Racket. And it would be great if the people that don't have experience programming in Racket could be sort of sprinkled around into groups where other people do have experience. It'd be kind of, I think, a hard thing if there's a group that was like everyone in the group was learning Racket from scratch right now. So, okay.
And my other question, which first real quick, if there is anyone without Racket experience, feel free to hit me up to be in your group.
Awesome.
But
Thanks, Franklin.
also, I was curious about like with the GitHub repos, if you know, like if you want us to just make those ourselves or if there's like a class repo that will be branched off of.
Yeah, I mean, so there is a repo that it's called the public student. Well, so I guess maybe I should go ahead and tell you there's a Google, not Google, there's a GitHub organization called, what is it called? The IU compiler course. Yeah. So actually here I can share that for a second. So here's the IU compiler course organization, which has a whole bunch of things related to this course. This Essentials of Compilation, that's the book. So that's where the actual LaTeX lives for this book. This IUP 423, blah, 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 fall 2020, that's our course webpage. You know, if you want to see what the markdown looks like for our course webpage, there it is. This private repo here, this course compiler, that's the instructor solution. So that's the code that I wrote and got help from lots of other grad students and stuff on. Okay, now this public student support code, that's the important one for you all. You're gonna wanna pull that down, and I guess you could branch to that if you wanted, or you could just copy over the files into your repo. Though I will be, from time to time, I will be updating the code in there, and you'll want to get a fresh, I may tell you, hey, you need to go back and get a fresh stuff from the public support code, okay? And that's, these other ones, course materials, I think that's where we put like old exams and things. Oh, and by the way, I will be making old exams available to you as practice exams. So, you know, you don't have to go to the frat, you know, back cabinets to find that stuff. I'll dig up the old exams and you can have them. I like to make new exams. And then, yeah. And then this support code for students, that's an old out of date one that we don't use anymore. So yeah, so that's the organization, the GitHub organization, and yeah, you'll be grabbing code from that public support code. Okay. Any other questions? And there's a link to that public support code off of the course webpage in the resources section. I also have some other resources there. There's like references on x86, on Racket, and a few other random tidbits. Okay. All right. Then let's go ahead and start talking about syntax and abstract syntax trees. All right, I'm gonna pull up my iPad. Hopefully that works. Can you all see my iPad?
Yep. Yeah.
All right. So perhaps the first thing we need to come to grips with in terms of programming language that we're going to compile is, you know, the data structures used to represent the programs. And the thing we're most familiar with is a textual representation of a program. Okay, that's the concrete syntax, right? And by text, I mean a sequence of characters, right? You've got your ASCII characters, one after another, you know, parentheses, you know, D, E, F, I, N, E, you know, and so on, close parentheses, right? We're gonna be, when we talk about programs, we're gonna be oftentimes writing out concrete syntax. But when we're inside the compiler, and when we're inside our brain, we're mostly going to be thinking about abstract syntax trees, okay? So just to give an example of these, you know, perhaps the simplest program ever is just the number 42. So there's the concrete syntax for a little program that produces the answer to life, the universe, and everything. And then in an abstract syntax tree, well, I literally mean tree as in like in discrete math, right? So tree has nodes and edges. And so here we'd have a node labeled 42, okay? And then maybe here's another bit of concrete syntax, maybe the read, a call to the read function. And then the abstract syntax for that would just be, again, would be a node with just read there, okay? And then you could put, of course, you can also have larger programs. So you might have sort of like something like -10 as a program. So this is saying, okay, I've got the number 10, and then I'm going to negate it, right? And so now this is now we start to see that this is a little bit more of the tree structure here. You've got a negative operation, and so that's its own node, and then the number 10 is another node there underneath it. Okay, so now we're starting to see we've got parent-child relationships between the nodes. Okay, we can also have programs with binary operators, like plus. Okay, so here now we're going to have a plus, a -10, and then a 5 over here. Okay. So we've got these concrete representations, that's the textual ones, and then we've got trees where the nodes are either operations, like plus, minus, or they're integers, okay? And we're gonna be using abstract syntax trees in the compiler a lot for the important reason in that the main thing we need to do in a compiler is when we're looking at a particular chunk of code, we need to ask like, well, okay, what kind of thing is this chunk of code? Is it a addition? Is it a subtraction? Is it a read? Right, so you can look at the tag or the label on the node itself to find out what it is. And then you oftentimes need to say, okay, what are your parts? What's inside of this? What are the subparts of this program? So for example, if I'm looking at this plus operator here, the subparts are gonna be, you know, these two subtrees, okay? So we've got a subtraction on the left and a 5 on the right, okay? And so the arrows, the downlinks in these trees make it convenient to go down and look at the children of a particular node, okay? So it's just a convenient data structure for the kinds of functions that we're gonna be writing in the compiler. All right, any questions so far about concrete syntax versus abstract syntax? Okay, so something that we're going to do a little bit differently this year is we're going to use, well, so let's talk about Racket, the Racket programming language. Okay, so you know, we're going to be writing our compilers in Racket. And so we need a way in Racket to represent abstract syntax trees. In the past, we've used S expressions. If you're familiar with that, great. If you're not, that's okay. We're not going to use S expressions this year. We're going to use Racket structs for the abstract syntax tree. The main reason for that is that it gives you a little bit better error catching sort of ability with structs. And also, it gives me more control over how they're pretty printed, which is kind of nice for your viewing pleasure. Okay, so for example, if we have an abstract syntax tree that's like the integer 10, what we're going to do is we're going to have a struct definition in Racket. So it'll be struct. It'll be called int. And so every struct definition in Racket, first you have the name of the struct. Okay, so this is a struct that's name is int for integer, and then after the name, you have sort of what's contained in the struct. Okay, and it can have 0 or more fields for for holding information inside the struct, okay? So this particular struct just holds one thing. It's the integer value, okay? So that's not that exciting. Let's move on to like a plus operator. So for operations like plus, say we had 10 and 5 maybe. Oh, actually before I move on, so we have this struct definition. So that just says, hey, we have this integer struct. Now, then to actually create like an actual node, then what you need to do is invoke the constructor, you know, which is the name of that struct, apply it to some arguments, which should be the same number of arguments as the number of fields up there. And that will actually allocate in memory a chunk of data and put the number 10 in there. Okay, and so then that's actually what creates one of those objects. Okay, so we call this is called an instance. The result of int 10 is an instance of a structure. Okay, and if you're familiar with like object-oriented programming, you'd call this thing an object. Or just in good old scheme or racket terms, this thing is a value. What you get out of that is a value, right? Okay, so then for operators, we're going to have a struct called prim. For prim, it means primitive operator. And it's going to have two fields, an op and an arg star. Okay, so op is for operator. The operator is just going to be a symbol. Okay, so this will be like, well, here, I'll do an example here. Prim, and I'll get to Jen Eyre's question in a second. Prim plus, so that's the operator there. And then you might say list, and then maybe int 10, int 5 to finish off. Okay, question from Jen Eyre.
Sorry, Tianyu had a question. I was just getting her attention.
Thank you.
Yeah.
Thank you.
So why do we use struct instead of as expressions here?
So it gives you a little bit better sort of error checking. So for example, the integer struct, if instead of giving it one argument, like the number 10, if you were to give it two numbers as arguments, it would give you an error and say that's the wrong arity. And similarly with the prim, if you don't give it two things, it's going to complain to you. Okay. And then I think I can also, I haven't done this yet, but I'm probably going to add some what's called properties, some contract properties to these things to get even more error checking to help catch bugs faster. So that's one reason. And then the other reason has to do with pretty printing. It turns out with S expressions, there's certain situations where the pretty printing was slightly ambiguous and somewhat hard to understand what was happening. And so I can control the pretty printing completely once things are as structs.
So is it basically the same as saying that the compiler code can be easily converted into, for example, type racket if we use struct instead of as expressions?
I don't know. I think that's an orthogonal issue.
Yeah. Okay, I have a doubt. Sorry, I'm not very familiar with structs in racket, but is int here a type specification or like just a tag, which is a symbol tag?
Maybe, well, so the int here, it's playing the role of a tag if you were doing S expressions, okay, or just a symbol. But it's sort of a symbol with extra goodness attached.
So it's like you have created some built-in types which will help us make it easier for error reporting and as well as pretty printing.
That's right. And so this struct definition here defines the name int.
Okay.
That's getting defined by that struct definition. And then as a result of that, you can say things like int 10, that's now, there's a function created that has the same name, that's the constructor. And then you can also say things like int value, you know, let's say I did a define, oops. Let's say up here I did define I to be int 10, and then I can say int value I, and that would return the actual bracket integer underneath this sort of wrapper.
It's a kind of a node in the tree, right?
Mm-hmm.
The
Yeah, I mean, think of the struct instances as the circles, and then and they might have things inside of them, or you know, like 10 or plus or whatever, and then also part of what's inside of them are the children, so the pointers down to the other nodes. So for example, with the prim, the arg star, so I'll oftentimes use star in sort of the regular expression sort of analogy, which means like many, 0 or many of these things. And really that means there's a list of things there. Okay, so that's why there's a list here when I was constructing, you know, this addition node.
Okay.
And then underneath it, there's more struct instances.
Okay, got it.
Mm-hmm. Maybe some more analogies. If anyone's familiar with the C language, these struct definitions are kind of like C structures, okay? Or if you're more familiar with classes, like in Java, they're a little bit like classes in Java, except that we just won't have any methods on these things. Well, that's not completely true, but I'm not going to be asking you to write methods on them. And by the way, all of these things live in this file called utilities.racket, and it's in the public student support code. Okay. And if you go browse in there, you'll see a whole bunch of struct definitions, and you'll also see the code that I've written to do pretty printing. And I've got it mostly the way I want it at the moment, but I'm still fine tuning the pretty printer to get indentation and things just right. So, cool. All right, so that's structs. Any other questions about Racket structs? Okay. The next thing I want to talk about is grammars. Okay, so hopefully you're having flashbacks to elementary school or high school where you, in English class, where you were diagramming sentences and things like that. So a grammar is a way to define a language, okay? So, I mean, maybe stepping back a second, what is a language? A language is in our setting, is a set of programs, okay? Some programs are in a particular language, okay? So we're gonna have, like, there's Racket programs and then there's C programs. And so, you know, the set of all Racket programs is one big set, and the set of all C programs is this other big set. I guess one question is there anything in the intersection of those two sets? I don't know. There's some pretty obfuscated programs out there. So
42 is in the intersection.
Well, I'm not so sure 42 is a C program per legal.
Oh, that's a good one.
Program. But I definitely would not want to bet that there's nothing in the intersection. So anyways, but yeah, so languages are sets of programs. They're usually infinite sets. Okay, there's an infinite number of different Racket programs out there, okay? And so how on earth are we going to define what it means for, you know, what it means to be a Racket program versus not a Racket program, okay? And the answer is we're going to use a bunch of rules to define the language, okay? Rules to define the language. Okay, and so we can use these rules both for the concrete syntax and for the abstract syntax. And so let's go ahead and I'm gonna define a language. I'm gonna call this R0, okay, for racket, and then 0 because it's like the simplest language that we're going to look at. It's so simple, we're not going to compile this language. This is the language that I talk about in the preliminary chapter. We're going to use R1, sort of a slightly bigger language, for your first assignment. Okay, and so we're going to give some rules. So rules look like the following. This is, by the way, this is we're going to use what's called eBNF, or maybe a variant on eBNF. BNF, this is, E is for extended, B is for Bacchus, and N is for Nauer form, okay? And that's what that sounds for. Okay, so exp, so our rules are going to look like the following. So exp is a what's called a non-terminal. It's going to be a category in the grammar, kind of like sentence or noun. We're going to have expressions, so exp for expression. And then this rule is going to say that an integer is an expression, okay? And then maybe somewhere else we define what integer means. Like, I'm just going to say it's like sequences of digits, okay? Look in the textbook, I talk about exactly what we mean by integers. So this is a rule, and what this rule says is that if you have an integer, a sequence of digits, you can classify it as an expression, okay? And then here's another grammar rule, which says that if you have an open parentheses followed by read, and here I mean the actual characters read, okay? Now, maybe I should be using, in the textbook, I use like italic to mark when I'm talking about sort of non-terminals. Maybe here I'll just do highlighting. And then and then I also usually use a TT, a typewriter font, for when I mean a literal, like this exact character, like READ, okay? So if you have a call to read, the read function, that's going to be an expression. If you have a negation followed by any expression, okay, that is also an expression. Okay, so notice that these rules are recursive. Okay, that's normal and okay. It's okay as long as we have some rules that are not recursive. That's how you get started building a program. As you down at the bottom, at the leaves of your program, you've got things like read, or you've got an integer, and then you can build up bigger programs using these rules. Okay, and then these, oftentimes you have lots of rules with the same left-hand side. Like in this case, we have exp. We already have 3 rules with exp on the left-hand side. It gets a little bit annoying to have to keep repeating that. So there's also a notation, the vertical bar, that's a way of grouping 2 rules into 1 rule that have the same left-hand side. So I'll do this with the plus operator here. Okay, so those are the rules for, well, almost all the rules for R0. Usually we'll also have a rule that says what is like an actual program, like an entire program. And for this little language, the whole program will just be an expression, okay? But sometimes a program might have other things in it other than just an expression. It might have a sequence of function definitions and then an expression, and so sometimes we'll have, what happens down here will be a little bit more complicated, okay? All right, so let's see an example of, this in action, and sort of how these grammar rules actually sort of can tell you whether something is in a language or not. Okay, so suppose I have a program -42. Okay, and then I ask you, like, is this is this sequence of text an R0 program? Yes or no? Okay, I'm seeing some yeses. So does anyone want to explain why it's an R0 program? And I think if you want to raise your hand, you can either wave at me, or I think there's a button also to click raise hand. And then I can call on someone. People are being shy.
Sam has a question, I think.
Okay, Zhao Zhang, go ahead.
Yes. So I'm not sure if this is right, but so according to the definition, expression is an int, can be an int.
Mm-hmm.
And then according to the definition, the express can be minus express,
Mm-hmm.
and express can be int. So this can, the minus 42 can be written as minus int, which is minus express, which follows the definition 3.
Exactly. Right. So what you just explained is corresponds to the sort of the drawing that I just did. Actually, let me make this drawing a little bit better. So we classified 42 as an expression using rule 1. So I can put like a rule number there. And then we classified negative 42, again, that whole thing as an expression, and that's using rule 3. And then we use rule 5 to classify the whole thing as an R0 program. Okay. So the way these grammars work is that something is in the language. So a program is in the language if you can piece together the rules in such a way that you justify it being an R0. Okay. And if you have a program where you cannot justify, by using the rules that it's in the language, then it's not in the language. Okay. So it's this very sort of positive thing. If you can prove it's in the language, it's in the language. If you can't, it's not. Okay. So that's how that works. And of course, this thing on that I just drew over here is what people call the parse tree. Many traditional compiler courses teach parsing, which is the process of turning a string or a text, a sequence of characters into a tree, and then into like an abstract syntax tree. Here at IU, we've been sort of skipping over that phase of the compiler for decades now, and skipping on to more interesting stuff. That being said, there is a lot of cool stuff in parsing, and I'm afraid you'll have to look elsewhere to study that. I think, was there a question from Jenner?
Sam had a question.
Thank you.
Oh no, I had my hand raised to answer the question. But
okay. Cool. Okay, let's also see what grammars look like for the abstract syntax as well. Okay. So now we're going to have grammar for abstract syntax. And what you want to realize here is that you could put together a big tree, a big bunch of structs in such a sort of random way that you don't actually get a real R0 program. Okay, so what this grammar is doing is it's saying which struct instances are really R0 programs. Okay, and so I'm going to use some of the same sort of categories, sort of non-terminals, except now the right-hand sides are going to be things like, they're going to have like struct names in them. Okay. So an expression is either an instance of the int struct or an instance of the prim struct, where you've got read, the symbol read as the operator, and the empty list for the arg star part of the primitive. Okay. And then we're also going to have prim negative followed by a list with an exp there. And plus, and a list, exp. Okay. And then actually for R0, we're going to have, there's another struct called program that sort of marks the top of the program, and it will have an exp in it. Color these non-terminals. And one little point here is that this thing here, if you go look at the program struct, or here, I'll write it down, struct, program, it has two pieces to it. It has an info and a body, okay? And so this, this empty list is the info part and the expression is the body. And for now, the info, we don't need the info thing. It's just an empty list. But further into the compiler, we're going to stash extra information that we need in that spot. And so this will actually be, there'll be like an association list where you can associate different symbols, like maybe local variables, and then associate that with a dictionary of variable to types or something like that. Okay, so we'll put various pieces of data in there that are useful during the compilation. Okay. So not just any struct instance will be an R0 program. It has to be an instance that was created, you know, with these in this particular form for it to be an R0 program. All right, any questions about that? Okay. All right, then let's move on. I want to talk about we know how to create these struct instances, these abstract syntax trees. We create them by calling the constructor of a struct. But then how do we use them? How do we, manipulate these structures? Okay. And you can, ask for a particular field. We saw, back here, you can ask for a particular field of a struct that way. But the more commonly what we're going to do is we're going to use pattern matching. Okay, so I want to talk about pattern matching here. I'm going to pull open Racket. So I'm going to share my screen to a different one. There we go. Okay, so here I've got, oh, actually I've got too many structs definitions. Oh, actually this reminds me of something I want to talk about. So I only created one struct called prim, even though there's really multiple different kinds of operator nodes, right? There's read, there's addition, there's subtraction. And so there's sort of as a compiler implementer, there's a choice about how you represent your abstract syntax trees. So I could have had a different struct for read, for add, and for neg, as you see in this file. I chose not to do that. I chose instead to sort of smush these different kinds of nodes together into just one struct, which is the prim struct. Okay. The reason why I did that is because sometimes you want to treat all of the nodes of a certain kind the same inside of your compiler, and you're actually going to see an example of this further down in this file. Okay. And so it just so happens that very, very often we're going to treat all of the primitives the same. So it's easier just to have one kind of node for that. Okay, so these are alternatives. We're not actually going to use those. Okay, so then the next thing we see in this file is I'm creating some instances. So I'm actually creating some abstract syntax trees there. E1, E2, E3, E4, E5. Okay, so maybe just to, oh no, my things are going a little bit slow because Zoom is a CPU hog. Right, so that program is just 42. This one is just read. It's a little hard to read the abstract syntax, minus, this is minus 42, I suppose. This one is plus negative 42 and 5. And then the last one here is plus E2 is read minus E2 again, read. Okay, so so we've created some abstract syntax trees. You should be, you know, in your brain, you should be envisioning little trees. And then now what I'm going to do is write a function that works on these trees. Okay, and I'm going to, this pattern is going to show up over and over again. It's called structural recursion. If you were in 211, you learned about structural recursion. If you didn't learn it there or somewhere else, you're learning it now. All it means is that you've got a recursive function. So here I'm defining the function, a function called height. It's just going to compute the height of an abstract syntax tree. And you can see that inside the definition of height, I'm calling height again, okay? But in particular, I'm calling height on children of the current node, okay? So when you're doing structural recursion, you're always doing recursion on the children of the current node, okay? The other thing that you always see with structural recursion is it pretty much always starts out with a match. So you're doing case analysis on the current thing you're looking at. So there's an expression E, we're doing a match. So this is how we're doing the pattern matching. Okay, and then we have multiple clauses. Each of these square brackets is a clause. The first thing in the clause is a pattern. Okay, so int n, that's a pattern. A pattern can be the name of a struct followed by a number of patterns equal to the number of fields in the struct. Okay, so the int struct has one field in it, so it has one pattern. This pattern n is a pattern variable, okay? And what's going to happen is that variable is going to get bound to whatever is inside of that struct instance. So let's say you have you know, the number 42 inside of this integer struct, n is going to get bound to 42. Okay. Oftentimes, you're going to need to use that n in the body of the clause, which is over here. Okay. This particular clause does not refer to n, just because we don't need to look at n to know the height of this node. Okay. And so the second thing here, the body of this clause can have any racket code in it. Okay, so you just put whatever racket code you want in there. It can refer to n, and you're good to go. Okay, so then down here we've got another pattern. This one is for the prim struct, and then we've got these pattern variables op and e star. Okay, and then down here you can see I'm using the variable e star here, but I'm not using the op variable. I just didn't need it for this particular height function. But you know, there's other, like if I was writing a compiler, I would need the op. Okay, and so here what I'm doing is I'm computing the height. So I decided that leaf nodes have height 1. I guess I could have gone with 0 instead, sort of an arbitrary choice. And then if you've got a primitive operator, what you do is you compute the heights of the children and take their max and then add 1, right? So that's just your standard how you define the height of a tree. And now I can run the height on all of these trees that we created. You know, I created up above, and lo and behold, you know, we get the right answer. The 42 up here had a height of 1. Read had a height of 1. This one, right, if you're thinking in terms of a tree, you know, you've got the negative as the root and then the 42 below it. So that's a height 2 tree. And then the next two programs have a height 3. Okay. So again, the important point here is that we're defining recursive functions that iterate over, you know, traverse an abstract syntax tree. That's what we call a pass, is a traversal over one of these trees. And then it's oftentimes we're going to be constructing abstract syntax trees as the output. That's what a compiler pass will do. But sometimes we're doing other things here where, you know, computing a number, the height of the tree. Okay, so when you go to write your compilers, you're going to be writing lots of structural recursive functions. If you're not writing structurally recursive functions, you're in trouble, okay? There are other ways to do it, but they're usually way more painful, okay? So you should just be doing, whenever you think, okay, I need to operate and do something to a program, you should be thinking, okay, I'm going to do structural recursion. Alrighty, and with that, this first lecture is over. I will take some more questions though, if you have them. But if you need to head off, feel free to head out at this point. Okay, any questions? Either questions about, you know, the structural recursion, the pattern matching, or anything's fair game about the course. Probably means I was going too fast, that it didn't have time to digest and ask questions. Do read the first chapter in the book. The first chapter in the book it goes over everything I've talked about, but in a bit more leisurely of a pace. And then feel free to ask questions about this material on Thursday when we reconvene. Just give everyone one more minute if any questions pop up. All right, well, definitely come with questions next time. I think we'll go ahead and wrap it up. Everybody stay safe and best wishes. And I hope you all have as much fun with this course as I did when I was a grad student way back when. So until next time, ciao.
Guys.
Thank you.